Here's a little practice writing and balancing single replacement reactions. The first thing I like to do when I see that there's a single replacement reaction is check charges. If I've got this reaction here and it's like chlorine, whoa, this might help. Chlorine plus sodium bromide. I want to know, like, what are the charges on all of these particles? Because then I'm going to need to know who's going to switch with who. Chlorine normally has a charge of -1. Sodium is normally +1. And bromine is -1. So the first rule of a single replacement is that like charged ions can switch. So I got to really know, like, what's the charge on my single element. My single element's going to be the chlorine. And then who's he going to switch with? Well, like charges can switch. So if chlorine is negative, it can only switch with bromine. Now, it would have been okay if I had like a -1 and a -2, or a +2 and a +3. The number of the charge doesn't have to be the same, but it's positive for positive, negative for negative. So because chlorine would form a negative ion, it'll switch with the other negative. There's step one. Chlorine is looking to switch with bromine. But step two, is that even gonna happen? Step two is that we gotta check this chart. We have to check the activity series. Now here we're dealing with halogens, so I'm gonna look at the second chart. And the rule is just that your single element needs to be more reactive than the one it'll replace. And so I find on my little halogen chart, chlorine, and he wants to replace bromine. A-okay, totally fine. The single element chlorine is higher or more reactive than bromine, the one he'll replace. So yes, this can work. In that case then, it's a go. We can swap the ions. And the first thing I usually do if I'm writing the products, if I were writing the products, I would just switch those element symbols. So chlorine's going to come in, bond with sodium, and kick out the bromine. So bromine is going to be single, and then sodium will bond with chlorine. Now, once I make those new products, I got to check a couple things. Number one, is your new single element diatomic? And the answer here is yes. Yep. All the halogens, when they're all by themselves, not bonded to something else, they are diatomic. So that is Br2. Then the second thing I got to check, if I make a new compound, we got to check the charges. We got to make sure that it's neutral, which this would be. +1, -1. Okay, so now I've got my skeleton equation. Now I've got this. But there's a lot that goes into that, right? I had to find the charges on all the elements. I had to figure out who's chlorine going to switch with. Oh, negative for negative. It's not that the single element always switches with whatever comes first in the formula. You got to check the charges, positive for positive, negative for negative. Then once I checked the chart to see that this would even work, the chlorine had to be more reactive than bromine. It was. Then we can switch the elements, but there's still a lot of work that has to be done. I got to check the single element to see if it's diatomic, and then I have to check the charges on my new compound. The balancing part, that's the easy part. Then once I've got that equation written, the skeleton equation, then I can go add the coefficients to make sure that it's balanced. That really is the easy part. But there's a lot of work that goes into these things. So here's some more examples. Let's try a few. All right, so first thing I want to do is probably find my charges. Now this first one might be a little bit tricky because iron is a transition metal, but most often his charge is +3. Now, if this were on a test or a quiz and there's a transition metal involved, I would tell you the charge. I'd give you a little hint where maybe it would say, like, in parentheses, by the way, iron forms ions with a +3 charge. Now, I can kind of figure out the lead. I do need to have page 98 handy in my textbook because I see NO3 is a group. It's nitrate. And so when I look up nitrate on page 98, I can find its charge. That whole group is -1. So if there are two groups of nitrate that are each -1, that means the total negative charge is -2. Then since there's only one atom of lead, the lead must be +2. So that one I can kind of figure out. But the iron I would have to tell you. Let's use +3. It's probably its most common charge. Why do I care about finding all these charges? Because I want to know who's going to switch. And so when I see that iron is positive, he's going to switch with another positive. Or you could think of it this way. All of the metals are positive. So a metal will switch with another metal. Non-metals are often negative. So if you have a single element that's a non-metal, it'll switch with another non-metal. Okay, so iron would like to switch with lead. Well, that means that iron needs to be more reactive than lead. Let's check. So I got a lot going on this chart. Maybe we'll kind of erase some of this. Here was my reactivity series for metals. So now I need to check, is iron more reactive than lead? Actually, they're right next to each other. Barely, but it is. Yep, the iron is higher than lead, so this reaction will work. This is a go. All right, so now we really got to work it. We're going to switch the iron and the lead. So lead's going to come out. Lead will be the new single element. And the iron's coming in. Iron will now bond with nitrate. So all I do is make that switch. I'm going to just switch the lead and the iron. I'm going to bond lead with nitrate, bond iron with nitrate. Lead is now single. Okay, now I have to ask two questions. Question 1, is your single element diatomic? Nope, not lead. No metals are diatomic. It's just some of those non-metals, and most of them are gases. So the lead is good. Lead is lead. I'm not going to change that formula or symbol. But when I make a new combination of ions, I have to check the charge. So this is going to be +3 and -1. So I'm going to crisscross or balance it to make it neutral. I need 3 nitrates. So subscripts like this 2 by the original nitrate, that does not carry over to the product side. Now the little 3 in the nitrate ion, NO3, that can come over. That's like its own group. But the 2 behind nitrate was only because nitrate was bonding to lead and lead's charge was +2. But now if I bond the nitrate to something else, it could have a different formula depending on the new ion. So now his new partner has a +3 charge, so I'm going to need 3 nitrate. Interesting. So in a polyatomic, you can carry over the little subscript. Nitrate is always NO3. But any subscripts that resulted from balancing one of your reactants, those do not carry over. All right, so now I've got to balance all of this. Oh, brother. This should take me no more than 60 seconds if I have all of my equations written correctly. So I see 1 iron, 1 iron, 1 lead, 1 lead. Gosh, this is great. Oh, dang. But on the reactant side, there's 2 nitrate, and on the product side, I have 3. Well, if I'm going to balance a 2 and a 3, my common multiple is probably 6. So if I put a 2 in front here, that'll give me 2 times 3, 6 nitrate. And if I put a 3 here, that would give me 3 times 2 for 6 nitrate. But also in the process, I screwed up the iron and the lead. So now I need 3 lead and 2 iron. But it's balanced. It should balance. As long as you've got those formulas written correctly, I guarantee they will balance. Cool. There she is. We got one done. Now, if you wanted to, you could put phase symbols in on the product side, and it doesn't ask for them here. And eventually, we'll talk a little bit more about those phase symbols, so I am totally okay leaving it as is. All right, let's try another one. We got to find charges. Start with all the charges. Chlorine is normally a -1. Sodium is a +1. Iodine is a -1. So because my single element would be negative, it's looking to switch with the other negative ion, the iodine. So again, it's not just whatever comes first, like charged ions switch. Okay, let's see if we can do this. Chlorine needs to be more reactive than iodine. Oh yeah, totally fine. Chlorine is higher than iodine. So this should work. We can make the switch. All right, so I'm going to switch the iodine and the chlorine. Just the symbols. So on my product side, I'm going to kick out iodine. He's all by himself now. I'm going to bring in chlorine. So sodium will now be with chlorine. Okay, so the 2 questions I ask. Is my single element diatomic? And the answer is yes. Yep, all the halogens, when they're all by themselves, they are diatomic. And is my compound neutral? Actually, it is. Fantastic. So now that I know I have the right formulas for the products, all we got to do is balance. Okay, so it looks like there's 2 chlorine on the reactant side. So I need 2 chlorine. Now that also doubled my sodium, but that's okay because I actually wanted 2 sodium. And look at that, they had a 2 in there. There's 2 by the sodium and 2 by the iodine. Yeah, I need 2 iodine. Normally, we would write those in ourselves. There we go. 2. Good stuff. 2 sodium, 2 iodine, 2 chlorine on both sides. All right, C is kind of a goofball. I don't know if I would give you it exactly like this. When water is in a single replacement, water acts like HOH. Whoa, that's a weird H. Water acts like hydrogen hydroxide. Where as far as charges go, the hydrogen ion is +1 and the hydroxide is -1. Calcium is normally going to be a +2 ion. Okay, so it looks then as if calcium is positive and it would like to maybe switch with the positive hydrogen. Gotta check my chart. Is calcium more reactive than hydrogen? Now, technically, it says this is an activity series of metals, but they do put hydrogen in because there are a lot of metals that react with hydrogen. Calcium is one of them. Calcium is way higher than hydrogen. So, yep, this reaction for sure is going to work. So I can make the switch. I'm going to switch only 1 hydrogen and that calcium. That's the goofy thing about these reactions with water on the reactant side. Water kind of acts like hydrogen hydroxide. All right, so let's put our products down. We're going to kick out hydrogen, so the hydrogen will be my new single element. And then calcium will come in. to bond with the OH hydroxide. So of my two products, I have to ask, is the single element diatomic? Yep, it is. Hydrogen is diatomic when he's all by himself. And of my other product, is it neutral? Well, calcium was a +2, hydroxide's a -1. Ugh. I'm going to need 2 hydroxides. There, I think I got it. All right, so now we're ready to balance. Oh, it looks like I have 2. Oh, well, I've got 2 hydrogen. And then I've got 2 hydroxides. 1 calcium. Well, here's where this is kind of handy to balance it as hydrogen and hydroxide. The calcium's all good, but yeah, on the product side, there's 2 hydrogen and 2 hydroxide. Well, then, yeah, we can just put the 2 right here. That gives me the 2 hydrogen that end up here, and the 2 hydroxide that end up over there, bonded with the calcium. And there we got it. There should be bubbles of hydrogen gas and calcium hydroxide produced. The last example, let's find our charges again. Bromine is normally a -1. Sodium is a +1. And chlorine is a -1. Oh, this one kind of looks a lot like B, doesn't it? Where there's a halogen and a sodium compound.
Brennan, Kate, to the main
Okay,
office
so
at this time.
if my single element is negative, it would like to switch with the other negative. Can bromine switch with chlorine? In other words, bromine needs to be more reactive than chlorine. But it is not. Bromine is less reactive. It's lower on this chart. So here's something that is just not going to work. Not all reactions result in a chemical change. This is a good example where all you have to write then is no reaction. You don't have to write any products. You don't have to balance it, because in reality there would be no products, and then there would be nothing I'd have to balance.